So, good morning and welcome to the European Imaging Academy webinar series. My name is Marie and I am your moderator today. Our webinar today focuses on the machine learning basics. But before starting with this, I would like to give you a brief overview of the company. Stammer Imaging has been a leading international supplier of machine vision technology for over 30 years. We are represented by 20 offices in Europe, Latin America, and Asia. With over 430 employees, we achieve a turnover of 109 million euros in the last financial year. One of the company's divisions is the European Imaging Academy, which I would like to introduce to you briefly. The Academy offers practice-oriented training courses on a wide range of vision topics. We offer our courses as face-to-face events in our training center in Puchheim, near Munich in Germany, in our subsidiaries, or also at your site. All training courses can, of course, also be held virtually. Our lecturers are experienced experts from the field. So and now I would like to hand over to my colleague, Phil Gralla. Hello, our presenter today, who will give you an introduction to the machine learning basics. During the webinar, you are welcome to post any questions using the chat function. Mr. Gralla will make some short breaks to answer those. So enjoy your webinar and over to you, Phil.
Yeah, also hello for me. Nice everyone is already here. And like my nice colleague already said, today I will talk a little about the basics of machine learning. We will introduce mostly keywords, explain the concepts, and give you well, an insight of this particular field. So what can you expect? The most questions I have is, of course, what is machine learning? So we're going to look into that. Then which kinds of machine learnings do exist? The task for machine learning. And I have a list of some example algorithms explaining which algorithms exist and why are there so many. So let's get started. What does machine learning mean? In the classic way, for us in the image processing, we work with data, mostly images, of course, and then we have a programmer, and he directly writes an algorithm that is working on this image to create some output. And that can be, of course, quite tedious. And sometimes the more complex your desired output is, the more complex your decision is, the more difficult it becomes for a programmer to actually achieve this task. And here is where machine learning starts, sometimes also called meta programming. What we want to do is, instead of directly telling the program what to do with the data, we program something called a learning algorithm that can take data as input, learns something from this data, and then is able to apply what it learned onto new data. And therefore, we shift the programming actually to this meta programming, the learning algorithms, and also are able to have it easier to apply for new applications. So that's a neat thing of the machine learning, and also why it becomes more and more popular. There are actually three main kinds of machine learning. The first one is the supervised one. That's the standard one and the one you will find most. Then we have the unsupervised one. That kind of machine learning is the one I get asked the most about, and that is what the customer wants the most, but unfortunately it's also the most difficult one. And then we have something that's sometimes referred to as in between, but it actually does not really catch what it is. It's a so-called reinforced learning. And to understand what these words mean, we will have some slides explaining each one of them. And just to give you a heads up, it is all these three exist And there are also some mixes in between, but we will focus on these three. And they also exist because they have different strengths to each other. Each one is more suited to solve a different kind of task than the other one. So let's start with the first one, the supervised learning, the most also probably classic one. And I always compared with when people went to school, because the supervised means that there's some kind of teacher, something that knows basically all the answers. I know not all teacher knows all the answers, but we just assume we have a perfect teacher here. And the idea is that we split into two tasks, two stages. The first one is the offline stage with a teacher, where we train our algorithm. And then later, when we apply it, we call it the prediction stage. And that is where we don't need a teacher anymore. So we have to we have to make sure that in the first stage, we teach our algorithm enough to work on its own. And for this learning, we need labeled data, images where we tell the algorithm what it actually sees. In our case here, I have this little cute bunny, and we tell the algorithm, here, that's a picture of a bunny. And then we want the algorithm to repeat what we just said. In our case, it says dog, and we said, no, that was wrong. I told you it's a bunny, so please repeat bunny. We keep doing this over and over until the algorithm responds correctly. And before you apply it, usually you will make some kind of exam where you give it data, but don't tell the system what it is, and check if the answers are as expected. Kind of a final exam. And then you use it. But the problem there already is you need this teacher, you need all this data that has all the information already, which can be quite tedious. That's why most people are asking about the next one. That's the unsupervised. So we want to get rid of this teacher. We want to have an algorithm that does everything by itself. And you can already imagine that sounds complicated. And so we don't have two stages anymore. We don't directly have a learning stage because we don't have a teacher, but the program has to do it by itself. But if you just give it some data and it can just do whatever it wants, it would just always give zero or just do nothing, because that would be fine. So it needs a task. You need to define a task, what the program is supposed to do. In my case, I gave it four. Or here we have four images, and we group it into two groups or different groups. And it sees it and says, well, I have three cats, one child. I will have two groups, cats and childs. If you look at it, maybe some of you were wondering, but why is it not grouping it into colors and non-colors, so black and white? You could also have that. And here already lies the problem, because usually your algorithm doesn't have concept. It doesn't know a cat or a child. It somehow has to work only with the data. And we as a human, we always have all these concepts in mind. And the program doesn't have it. So you have to be very specific with the task, and you have to be careful because the outcome might be unexpected. And that's what makes it so difficult to work with it. And for some people call it a workaround. I prefer to see it completely as its own, as so-called reinforced learning. If you look at it, the picture, the explanation looks almost the same as teacher. The important part here is we have something called an environment, somewhere where the algorithm is kind of living in. And the difference is we are not going to school anymore, but instead we drop our student in the wilds in some forest, and it has to survive on its own. The jungle doesn't care if you live or not, but it gives you feedback on what you do if you survive or not. So if I eat a berry and I feel sick afterwards, I have to learn by myself, this berry isn't good. So that's what we can call an environment, something that gives the response to our action. And typically, for example, driving a car. So if I drive a car, my response is I can still drive. I crashed the car, I hit someone, this kind of response. And now I have to be able to make my own conclusions from it. And we want to, or usually when we do reinforced learning, we still split it into two stages. And the reason is quite simple, because we could always do it directly in the field. But if you have a factory and you want to have an algorithm learn on the job, there's going to be a lot of trouble. So instead, what you have is you have some kind of environment. Maybe you modeled it in a computer and you have a simulation running, or for cars, for example, maybe you have a little practice field where they can just drive around. And when they learn enough there, then you will proceed to the next stage, the online stage, where you then start doing your predictions in reality. And maybe if you think about it for a moment, defining such an environment to make sure that it is will be have enough information and all the variables that the real world has is quite difficult. So also this is a problem. And the teaching, of course, already sounds more complicated because the algorithm still has to make some decisions based on the feedback it becomes, if it is good or not. So that is the three main kinds that we have, and each one of them is more suited for a different type of task. And we will now proceed to the task. And after all these tasks, I will have a short break where you can ask some questions. Okay, so the first task is classification, very actually kind of simple. You get a picture, an image, and you have to decide what do you see on this one. And you have a list you can choose from. In our case here, my list only has some names, panda and red panda, and the image then has to be sorted. This image is a giant panda, the one is a red panda. Kind of only yes and no in a way. The next one is a regression. It's similar in a way that I again get an image, and now my decision is not just like cat, dog, or car, but instead I have a range that I will return. In my case here, I get a confidence back, so a value that can range between 0 and 100. And here we have our little image, and we say, well, 70% I'm sure it's a dog, 3% I'm sure it's a cat, and yeah, funny enough, that actually is a true example is dogs and cars look for computers similar. So we have 15% chance for this one looks a little like a car. And you can take this one as the regression there, or you can now make a decision based on this regression. So say like, well, dog is obviously most likely, so it must be a dog. And then I can also do a classification again. So these two are linked with each other and sometimes also interchangeable. The next one is the so-called clustering. So we want to find groups. And here I have just random data points in 2 dimensions. So each of these spots you see is a random point. And I gave it to feed it to an algorithm here at STEM, and the algorithm is specialized in finding patterns. And then it returns, I find 3 main patterns. That's the 3 spirals. And you might be able to see it on your screen. There is this turquoise color stuff. The fourth group is something that doesn't belong to something. It's just kind of a trash class. So it says everything not here, some outliers I put into there. So I can find these patterns. And of course, I get asked a lot, well, this one doesn't seem to be very useful. And you're kind of right. I don't need to find the spirals. But the idea is that this concept of finding a pattern inside these data, I can also apply to much higher dimensional data, in our case, images. So here we see some examples. We have 4 images and we find 2 groups. So one group is the dogs and one group is our elephants. And this way, by doing some abstraction, we are able to actually cluster these groups. And this one is an example that you can do unsupervised. This clustering can also be used for something else. So I had a lot of animals. I like animals. I'm not so good with fashion, but my wife said, Phil, you should learn some fashion. And since I'm not good at deciding what is what, I trained an algorithm. This one is a data set provided by Zalando. Everyone can use it. And it has different classes. So you see t-shirts, trousers, pullovers. And you have to differentiate them. But what I wanted to do here is I feed it 2,000 images of these 3 classes. And if you pay attention, maybe 1 or 2 of you notice there's 2 things that are not quite right. 2 things don't really fit into. And the algorithm then told me here, look, I have standard examples on the top. This is I think 2 shirts in a way. So these ones are normal. It says, I know these ones, they're quite all right, but then you have 2 images that don't really fit. And that's the bottom ones. So it finds outliers or novelty inside the data set and tells you then these things don't belong to it. And that is something also interesting, of course, for application in industry. You want to find the things that mess up, things that fall onto your factory belt, or stuff that's just broken. So these algorithms are used for that. Another typical task for machine learning is segmentation of images. So you have an image, and now you want to segment it into, in this example, fore and background. So we want to find the dog, And here I used an algorithm that just separates fore and background, and it finds then the stock. And you can see you can either have a mask, or you can, for example, gray out the background and therefore have better contrast or stuff like that. Good. We have one more task that is also quite commonly asked. It's object detection. And this task actually is a combination of two different tasks that we had before. So we have to find an object in an image and also decide what kind of object it is. So we have regression and classification. In our case, two examples from our software: finding letters and then decide which one it is. And the other one here is finding the name of the company on the pens. And for the last example, this one is an upside down pendulum. So it's a little card, a wheel card that can be pushed and dragged forward, backwards. And on top it has this weight. And if it's perfectly in the middle, the weight will just stand there. But as soon as it moves a little, it has some kind of angle, it will fall down. And the task is now to move the card around so that the weight will not fall down at all. And it's a very typical task for reinforced learning, for optimal control. And it sounds a little mathematical, and actually you're right, this example is very much for an academic purpose. But if you have a storage place with very high ceilings and you want to put the storage on the top and have a small robot on the bottom, you will run into this kind of problems, for example. So even that will have some kind of applications. Okay, so a short summary. So far, what we have is we looked into the supervised, unsupervised, and reinforced some tasks. And before we go now into the algorithms for the machine learning to solve these tasks, you have some time asking some questions. We'll see my colleague will read it to me if there's any. No, okay. You will have some more time, of course, at the end to ask questions. All right, so everything so far we have seen what is machine learning, how we can solve it, what tasks we can do to solve it, but we don't actually look into how to solve it. And the very most prominent one nowadays, of course, are the artificial neural networks, also ANNs, and deep learning. So these networks are, yeah, probably the one you have heard the most of, and they are quite powerful. But what do they actually do? So the idea is you have some input, these red dots, and each of these red dots represents just a number. So if you have images, then each pixel is a number, some value. If it's an RGB value, you would actually have three values there. And so you have a very long list of inputs, and then you so-called feed it into the network. So each of the inputs is connected to something else called a perceptron. It just sums up all its inputs and then generates a new output number. And you can put a lot of these layers, you sort it into kind of layers, and you just stack it and stack. And at the end, the final one, the output layer, makes your decision. The ones in the middle we call hidden layers because they are not obvious to, if you look at outside, because you have only an input and an output. What happens in between, you don't see. So that's why they're called hidden layers. And if you have more than one, we talk about a deep learning approach. And here you see a fully connected. So everything is connected with each other. And to have it more robust, to have it better suited for different kinds of task, there's different architectures. The main idea is still the same, but now we have some extra connections, or we just keep some connections, uh, like not have them at all, in order to have this kind of architecture that is more suited for tasks. And the most common one in our field is the convolutional neural networks. They are for image processing. We also have these GANs, they are generating, can be used in a way for dimension reduction, but they are also used for denoising an image, for inpainting, generating new images, and also for the typical AI, like AlphaGo is based on a GAN. Then we have memories that have kind of networks that have memory, so they can save some information in a way. And there's, for example, long short-term memory networks used for language. Transformer networks are also used for that. Recurrent neural networks, all these things. And then we have some special, some odd networks, the so-called self-organizing maps. And they're a little different than the rest. And they are actually the only ones that are really unsupervised. So the other ones, sometimes you will see, are kind of doing unsupervised tasks, but actually they are always doing supervised or reinforced tasks. So you have to find someone gets this data that it can reproduce. And the only ones that are really unsupervised are self-organizing maps, and also the ones you will find the least because they're quite different from the rest. And but for completeness, we have them here. What else can you do? So these neural networks are very nice. They can do a lot, but they will always need a lot of training, a lot of data. So that's an issue that you will run into, especially if you're a medium or smaller size company, and you cannot afford to have some students doing 1 year annotations for you. And there are some other methods that support vector machine, which is actually newer than neural networks, but was applied earlier. So neural networks, the idea is quite old, already from the 60s, but due to computational limitations, they were not really used. And the support vector machines were invented in the 90s. And so they were used before. It's a method from linear regression. And here's an example. We have two classes. You can see the red and blue ones, and you want to separate them. And the solution is this separation circle. And some people of you might already notice the circle is not really linear, and you're correct. So what we do is in this way, we do a kernel trick. So we map it into higher space called feature space. There we find this hyperplane, it's called, so a plane that just divides the two. And when we go back to our space we had before, then we have this decision function, which in our feature space is linear and non-linear in the output. And these ones can also be used right from the beginning as one class or unsupervised method. So that's also quite neat. And they usually don't need as much training data as your neural network. Okay, so what else can we do? And one simple idea, and an idea that has been done a lot, also is probably the most natural one, is the so-called k-nearest neighbor. So we take examples that we already know, and then we get some new input, and we compare to all the examples we had before. And in our case, we have two classes. We have the dots and triangles, and now we get a new one and we just lay them out and look, okay, what is closest to you? And the four neighbors are not circles, triangles. So our decision would be, by your neighborhood, you should be a triangle too. And this one is very nice. It can work quite well. But the problem is, first of all, you would need to save all the information that you use in the training. Right? That's one problem. And the other one is defining what is a neighbor can be quite difficult. If you think about pictures, images, and we want to compare one image to the other, just compare pixel-wise might not be a good idea because you just have a shift of 1 or 2 pixels and all of a sudden the image looks completely different for the program, but they're actually the same. The other one is some people say, well, if it's an animal, we just look at the fur and like, that's a good idea. But how do you describe fur to a program? Then you would need to program that one first. So that's very difficult. And in order to avoid this situation, we use actually the other methods I showed before as a substitute. They still have this idea of learning from neighborhood, but they are also learning what it means a similarity. What is similarity? Okay. And another approach that gets more and more popular and has some nice results is the gradient boosted methods. And our example here, gradient boosted trees. And many algorithms, also the neural networks, they get more and more complicated, more sophisticated. They can solve better things, but they're also a little bit more difficult to understand what's happening, especially if they don't work. Why? And that's a reason people came up with the idea to, well, we use simpler models. Models we understand, models we know what's happening and also maybe have more control and stack them. So not just have one, but many of them. And that's where the gradient booster comes. So we have our input data. We have a simple model which explains some of the data, not all, it's just some, it's simple. And then we have another model that works on the prediction from the first one and on the original data. And then we stack them one after another. And this way we get a much more complicated decision, but based on very simple models. I have an example here how it works. Here you see a sine. Actually, it's a couple of sine functions, and we want to approximate it with only the stepwise function. And on the left, you see the approximation. On the right, you see how the error gets reduced by each model. I can start one more time. So you see this on the right, the error, and the model then trains on this error, and the overall is on the left, and how it gets better over time. While the single model is quite simple and is able to approximate this function very sufficiently. You can mix this one. It does not have to be only the same model. Like here, they also don't need to be decision trees. They can be different kind of functions, even neural networks you can stack this way. And yeah, that's why they become more popular recently. Good. So we do have three kinds of the machine learning: supervised, unsupervised, reinforced. Again, each one of them is more suited to solve a different kind of task, and we have a whole bunch of algorithms. And the question I always get is, why do we have all these algorithms? Why is there not one that can solve it all? And the answer is each of these algorithms has some strengths and some weaknesses. And the best thing you can do is actually look at the circumstances and your task and then decide what is best suited for me. So each one of these algorithms uh, is better in a different field. So while the neural nets are very good, if you have a lot of data and you want to be sure for the prediction ones, they're good. But what happens if there are some values missing? So if you have images and for whatever reason, because of the way you take these images very fast, you might miss lines in between. These neural networks might not be the best choice. What is if I don't have many examples? I want to train error classes, but of each of my errors, I only have 10 images. Then a neural network would also not be a good choice because it needs a lot of data. And even if you enhance it, try to make more of the same data, it will still be in itself be the same image. So that can lead to problems, and some other one might be better. If I have a lot of data, then the k-nearest neighbor might also not be a good idea because I need to save all this data for the training. So you see there's a lot of different algorithms, and therefore you as maybe the engineer as a company, when you want to apply machine learning, you also need to know what you want to do. That's also a very important question. It's not just I want machine learning, I want to do deep learning, but think about what do I want to achieve and what do I actually can provide to achieve it. And then you can pick which one is your best approach. If you want to learn some more about this one, about the machine learning, we here at Stemmer offer, of course, our own software, but also we have training center here in Puchheim where we have trainings of various lengths, can be hours, can be days. You can choose that one where we go into more depth. We show the different algorithms, we show software that can solve it, examples. You can also bring your own example. Of course, nowadays, with the current situation, in-house is not the best choice. So we also offer these things online via Teams or other means of online communication. But still, if you have a problem that you would like to solve, if you just want to know more, you can contact us. You can also yeah, tap in the resources of the Imagine Academy, and we try to help you. All right, so that's all for me. Thank you very much for your attention, and we now have time for questions.